Hi guys, this is usually 5 and today I'm covering the core idea of exponential smoothing and all the models falls under the exponential smoothing principle. So let's start the video from the introduction of exponential smoothing. Actually, exponential smoothing is the technique for forecasting the time series. We already know about this, and the exponential smoothing is based on the principle of the recent observation are more relevant than the older ones for the efficient forecasting for the accurate uh, model results. Yeah, that's the main core principles which the exponential smoothing based on. And why exponential smoothing? Why it is named as this smoothing is named as exponential? Cause basically it works on the weightage average, and it works on the weighted average, and it give more weights to the recent observation rather than the older ones, and the weights for the observations decrease exponentially as the weights for the the latest observation will be more in comparison to the older observations, and it was the core principles in which the weighted average works, like it provides the weights to the different observations based on its time. Yeah, the same thing work on the exponential smoothing also. Yeah, let's see types of exponential smoothing. We will be covering about simple exponential smoothing and Holt's linear trends, the smoothing, and Holt's winter trend. Yeah, Holt's winter seasonal uh, smoothing. This will be covering in this video. We'll cover this all in here. Yeah, as I spoken all about the principles and the basic concepts of the exponential smoothing. Let's see. Yeah, weight decrease exponentially as the observation get older. That I already spoken. This is a contrast to simple moving average, where all recent observations are weighted equally. Yeah, the simple moving average used to treat all the observation equally gives equal weight to the older and the newest data, and calculate the moving average and predict the time series. But the things is opposite in here, just opposite in here, that it weights gives weight in comparison with based on the time. Yeah, let's dive into the simple exponential smoothing. Where we can use the simple exponential smoothing is if we don't have the if we don't have the seasonality in the I'm talking about the time series where there is no clear trend and seasonalities, and the data should be fluctuating around the stable means the trend is should be like sideways trend, not upward and not downward. That's the use case of the simple exponential smoothing. And diving into the intuitions of the simple exponential smoothing is uh, Like imagine you are trying to predict tomorrow's temperature. Your best guess might be the combination of today's actual temperature and what your previous predicted today's temperature would be. Like it works on the combination of the predicted value, current predicted value, and the current actual observed value. That's the how the simple exponential smoothing works. All other exponential smoothing techniques works on this basis, but the simple exponential smoothing don't consider trend and seasonality. That's the major difference between SES and other smoothing techniques. Seeing the mathematical foundations as this is the major expression for the simple SES, and here we are predicting the here in the forecast for the next time period, and alpha is the parameters, smoothing parameter whose range is from 0 to 1, and uh, increase the higher value of alpha gives more weight to the actual observed value, and less weight to the predicted time series, current predicted, not the upcoming ones. Yeah, we have understanding the alpha. If alpha is close to 1, the model gives the lots of weight to the most recent observations, means the actual one rather than the predicted one, and very little to the past forecasts. Like the forecasted, we denotes the forecast with the cap YT cap, and the recent observations is normally YT, and the model give the smoothing techniques gives more priority, more weights to the observed value, not the forecasted one. It makes the forecast very quickly to change, but it can be nervous or volatile. Means it it will not the latency will be quite low using using this smoothing technique, but it is nervous and volatile, means it won't work, like it won't stay for long. It is if you provide no, I can't say that. If you uh, if you don't have the current data set which you are currently working on, and if you then the value, the actual forecasting value won't be there, and that's what we call as an volatile. Yeah. Another one is if alpha is zero, just vice versa, just opposite of the first point, that if your parameter alpha is close to zero, then it will give less weight to the observed value and more to the our forecast value, recent forecast value, not the upcoming ones. That, but we are forecasting the upcomings. The exponential in the name. This is why it's called exponential. We can expand the formula. We have in plus two level of mathematics. We have read about the binomial theorem. In that topic, we have covered. We expanded the lot. We have extended the expressions till the n terms, and the same ideas, same concept is here, and all notations are not much. uh, we need to understand ourselves, we need to observe ourselves. Our notation is not a big deal for here, but the expressions, how it is working is the basic mathematical foundations is here, and expanding on the expressions results uh, this is the final results of the expand. This is the expanded form, which is the final result for the n different observations. Yeah. Why the means here the alpha value of alpha decrease exponentially. That if you squared, if you exponents the small value, then it will be more smaller than in next step, and it goes and goes and goes and like that, and that's how the older data, the older values get less weights. Okay, let's shift into the another methods uh, of exponential smoothing, which is called as Holt's linear trend method. Yeah, we can generally clear by seeing the topic also, like it's what trend has been mentioned in the topic in the, so that we can assume, we can make sure that and this model, this method will only work on trend, not on, but not on the seasonality. Use case, in the use case line it has been mentioned about it won't be working with a seasonality but works on trend, and we call it as a double exponential smoothing. Why? Because we, I think we have two expressions, two equations for this, or three, let's see here. Yeah, we have three, but this forecast equation is normally the final combined form of the level equation and trend equation. SES can't keep up if the data is consistently increasing or decreasing. Hall's method extends SES by adding a second component to be smooth the trend. Yeah. Uh, how the Holt linear trend method is different from SES is it has another component. It extends the simple exponential smoothing by adding the second component, the trend, and that's the only difference between them. So now we are tracking both the level of the series and the trend of the series. Yeah, we level, and we are tracking in the SES. We were tracking only the level of the series, but here we will be tracking trend with side of the level of the series. Let's get into the mathematical foundation. The level equation is shown in the screen, not more different of from the SES. As same as this is then observed value, and this is the parameters, smoothing parameters, and same, but what difference from the above is just added the bt minus 1, which is the trend equations. uh, yeah, that's the major difference in between the level equation and the uh, things, the trend equations expressions is also here. This calculates the smooth trend at time t. It is weighted average. Oh, sorry, I haven't shown you the plot of the SES. Okay, let's first go there, and then we'll be covering the remaining one. Here is a code. I have already code. I have written the code already, so that I can make the video as and not long. I can make the video not long. Here is a simple exponential smoothing SES, and I have imported it from the stat model. Stat model is providing uh, the simple exponential smoothing, Holt exponential smoothing, all the functions, all the things. So I have imported from the stats model and just called it here. Where it is, yeah, here, just introduce in the functions here and pass the training data and fit it, and then the logic behind this line is why we added the length of test is how much we want, how much forecast we want, how long we will be forecasting the data. Means if and as long as the test sets end, we're gonna continue forecasting. Yeah, that's the major logic behind it. The it forecast. Uh, if you have the test sets of 50 test sets data, then the this simple exponential smoothing will forecast the 50 more values. That's it. And talking about the plot, I have plot from this is an our plot. First let's see the index. Here blue line is a trend and orange is test, as we have green line represents the SES forecast. Here you can see that SES has forecasted the value without considering any the we already learn about that SES one considered when works on the trend and seasonality. So that's the you can see the results. You can see visually here that it haven't considered the trends and seasonality. Here the straight lines has been plotted traced here. Yeah, we haven't test data in seasonality, more about seasonality here, but our SES model haven't forecast the seasonality. Yeah, okay. Others will be seeing soon. Yeah, where we were last time. Yeah, trend equation. Yeah, trend equation. It's weighted average of the most recent change in labels and the previous trend estimate. This is the whole equations of the trend equations. What is calculation of trend at time t? It's a weighted average of most recent changes. Yeah, weighted average of recent changes means how we used to calculate the weighted average means multiply the individual observations with the weights and divide with the sum of the weights. That's what uh, moving weighted average is. And here we are calculating the weighted average of the differences between the recent changes. And beta is generally smoothing parameter for the trend. As alpha works for the label, beta works for trends, equation trends. uh, yeah. You can see not more difference. Okay, if you like if you want the analogy, then in place of alpha, beta has came, and in place of yt, that recent observed value, it have come the difference between the range, and adding the same as the 1 minus alpha to the forecasted value. This is the previous trend. What was that? We'll be seeing in these plots only. And the at final stage, the forecast equation is the combination of both level equations and trend equations. That summation is adding level equations and adds into trend equation. Here is what adds represent is the number of period ahead to forecast. How much period we gonna forecast the time series? That's what H is representing. Let's get into the code for the Holt linear trend method. Here I have where it is. Yeah, Holt linear trend. Yeah, no more complexities in the coding section because Stats model has provided us the Holt method Holt function to perform the forecasts. So yeah, I have called The function here pass the trend data and the forecasted it with the test length of test series. That's the main reason, and let's dive get into the chart. We have Holt linear forecasted represent with the red lines, and look at here how it is different from the SES forecast. Like it have considered the trend also. You can see that it is quite a uptrend, quite in uptrends direction. Yeah, I think from here, yeah. If you see like here is an uptrend and as similar to that, the peak values has raised from here. This I think whatever no why it hasn't considered this peak as it is actually a weighted average, so it comes in it. I can show you the weighted one here, but it is also seasonal knife. Where it was, yeah, I think here weighted this chart with WMA, yeah, forecast represented, yeah. This is how it is calculating the weighted average and comes the linear one as similar as the working process is in the backside is same. That is, I've considered the trend, but in above charts it haven't considered that. It is we know the main properties of linear forecast is generally considering either a combination of the label equations and the trend equations only, so it haven't there is no considerations of the seasonality. Seasonality will be covered by the Holt-Winters forecast. There is two methods for the Holt-Winters. That one is additive methods and another is multiplicative model that we have talked in the time series. In the introductions of time series, there are two methods, that additive and multiplicative methods. Before I think time series decompositions. Yeah. Okay, let's get into the what we have already discussed about this, and let's dive into the Holt-Winters seasonal method. Yeah, here seasonal has been included in the topics only in the terms only. Triple exponential. Last time we studied about double exponential called all linear trend model, and this is seasonal. Means why triple exponential means it have covered all level equation, trend equation, and our seasonal equation. It will be covering all three. Why double exponential in the all linear? Cause it covered the trend and our level equations. So yeah, that's the main reason for for telling the double, triple, solo. Yeah, that's for forecasting time series data we have with both trend and seasonality. Yeah, that's how I have taught. I told you monthly sales data that grew year over year and have peaks every December. That's what seasonality means. We already know. Intuition, this method extends halts by adding a third component to be smooth is seasonal component. Yeah, we already have the trend and what level equations, and what actually Holt-Winters seasonal method doing is just adding the third component seasonality for to include the seasonality and to forecast good one. Yeah. No more different than the simple forecasting, just considering they considered other components of the time series also. That's the major difference between them. The method actual third components to be smooth or seasonal component. This component capture the repeating periodic patterns in the data. Yeah, that's the definitions of seasonality only. There's two variation based on how the seasonality interact with the label and the trend. Okay. Let M be the length of seasonal period. That is, for example, m equals to 4 for quarterly data, 12 for monthly data. Means how the seasonality is repeating in the time series, that is mentioned, that will that the m is representing. If you provide the the four value of m, then it is what is it separating that uh, uh, it thinks that the model thinks that the seasonality comes quarterly, and so on, according to the value that we have provided. Yeah, first we will talk about the additive model and then multiplicative model. How they will be working differently, we'll talk later. When to use seasonal fluctuation are roughly constant in size. Fluctuations are constantly roughly in size means uh, roughly constant in size means your fluctuation, your seasonality's value are fluctuating over the time in the equal. Like if your graph, if your amplitude for the uh, time period at time t is 1, then after a time t plus n, then the range of the fluctuation is the amplitude would be the same, that is 1. In that case, in that scenario, Holt-Winters additive model works well. Otherwise, you can use the multiplicative model. No, I can't say that, but multiplicative model is generally works for the proportionality. Like if yeah, then generally, yeah, the drawbacks of the addition models will be covered by the multiplicative method. That's what it is. Uh, Regardless for the level of series cells, here example is also given. A sales always increase by 100,000. That's what I have told, like 1 as an amplitude. This 100,000 unit is also an amplitude from the baseline, where baseline cells are 10,000 or 20,000. Yeah. If your baseline sales is 20,000 or 10,000, means your I'll show you here. Suppose if you draw the, okay, let's see here, this is the baseline here, and the baseline sales is almost around the 9,000 or 8,000. Yeah. And the seasonality, how seasonal, how you can see the seasonality is from this here, how much amplitude, the first amplitude is gone down, that is, okay, if we are in the 8,000 range, and if the amplitude is combed over this one, if you subtract between, if you calculate the range, means 8,000 is the uh, fluctuating values over the uh, seasons, that's the seasonality value. And where you can see it in uh, 2011 the seasonality remains same with and moving over the time, coming into the eighth month of the 2011, the same range of seasonality, and going up to the last month of the year also, the seasonality value remain, the seasonal fluctuations remain constant in size. And here the addition model additive method perform well. Mathematical expression is not more that complex, let's understand. Level equation, here we have deseasonalize, means firstly we will be removing the seasonality and uh, derive the level equation. Afterwards, subtracting the level equation, I think here forecast, no, seasonal expression. Yeah, subtracting the level equation with the forecast without the value will again derive this seasonal equation separately. Yeah, no more difference. Trend equation is same as it have worked. It is the extended extensions of the linear model, linear method. Seasonal expression. Seasonal expression here, the new is this one, seasonal expression only. Seasonal expression works on the parameter of this component weighted average of current index and seasonal index for the one period ago. Yeah, that's what. No more difference between that. You can analyze with the normal level equation, like it is as an yt and it is 1 minus alpha and it is the forecast value. That's the analogy, not still analogy, that comparison. Forecast equation is generally addition of the what addition of our label and trend, I think. Yeah, label and trend plus seasonality. Yeah, how we have done in the time series decomposition, same thing, same process we are also doing here. That how we used to decompose the components of the time series is, we used to add the trend, we used to add the seasonality, we used to add the noise residuals, and the final packet, the single packs was the total additions of all the components. As same as that, here is also same for the forecast equation of exponential smoothing, winter seasonal methods, triple exponential uh, smoothing. Yeah, and multiplicative model is quite different from the additive model, because proportional to the level, like they are in percentage. Sales always increase by 20% in summer. Means if your sales was 10,000 in previous the summer season of previous year, then the sales will increase by 20% this summer. Yeah, in that case, in that scenario, the multiplicative model will work. Mathematical foundation is as same as that, but here in the level equation we have subtracted and added, but we won't be doing the same, but we'll divide the observed value with the seasonal values, and other is same. Trend is remain same, and here is instead of subtracting, we are dividing the observed value with the level equations, and no more difference. Another major difference for the forecast equation, adding the trends equation and the linear level equation, and which we are multiplied with the seasonal equation. That's the major difference between them. And yeah, we are at the end of the video, and some we have the summarizations of the all the methods. uh, let's summarize it. In SES, the SES doesn't consider the trend and seasonality use case. If there is no trend and seasonality in your time series, then you can simply use the exponential smoothing. Here in this case, oh, okay, let's talk a little about the winter forecast, seasonal forecast methods chart. Yeah, this purple chart, purple graph is showing representing the Holt-Winters forecast. Look at it. Look at into it, that it have considered trend and seasonality, like at equal interval of time. The what is seasonality? Seasonality comes with the equal interval of time every and certain time frame. Yeah, and that's, we can see it. I think it is weekly. Yeah, weekly. I think I have mentioned 7 year where it is. Yeah, seasonal period means 7. That is weekly seasonality. Repeat weekly. And seasonal ad, this is the, we are defining the methods. Which method we are using is that additive method. This is it representing that, and passing the trend data for the training. Yeah, calling the function and trend here we have plotted, and let's see here. Consider what trends and what we have seasonality. Yeah, no more than that. Okay, as let's summarize it. Key parameters used in the simple SES is only alpha. Alt linear there has two parameters, alpha and beta. A alt linear trend only work for trend but not in seasonality, level and trend. Holt-Winters additive works for the trend and constant additive seasonality. Three parameters are introduced in the model. Holt-Winters multiplicative models also has same but work in the proportionality situations. Yeah, parameter is the same equal to the Holt-Winters additive, no more than that. Yeah, here is the end of the video, and whatever. In practice, the smoothing parameters and initial value of level, trend and seasonality are not picked by hand. They are typically optimized by the computer algorithm that minimize the forecast error metrics like MSC on the training data. What? They are typically optimized by the computer algorithm that minimizes the forecast error matrix. Means we won't be passing the value weighted value like weights value, like we have passed the weights in the weighted moving average, like we have 1 2 3 in such a way, but we won't be passing the value of parameters by ourselves, but it will be optimized by the counter algorithms. I haven't understand this MSC pattern. Okay, let's end the video here. Yeah, thank you guys.